Okay, here we are. Example 1. Use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the given curves about the y-axis. So we are going to revolve this around the y-axis. So let's go ahead and sketch what this thing is going to look like. All right, so we've got y equals x cubed, which looks something like this. Let's see, we are bounded by y equals 0, which is the x-axis. We are bounded by x equals 1. Call that x equals 1, and x equals 2. We'll say that that's x equals 2. So it looks like this is our region right here, and we're going to revolve that around the y-axis. Now you might look at this one here and say, well, I could actually solve this one for x, because x would just be the cube root of y. Yes, you can. And this one actually can be done by using our traditional disk and washer method. It's a little bit more challenging, and as a matter of fact, I have done a supplemental video already showing you that you can do this using the disk and washer method. So if you want to go ahead and watch the supplemental video just so that you can see that it works out the same way and it can be done the other way, go ahead and do so. But for this one, we're going to do the method of cylindrical shells because that's what it's asking us to do. So it looks like, if we were to kind of draw what this thing looks like, rotating around the y-axis, it looks like we're going to get something on the other side, which kind of looks like this. And then it's going to come around here like that. Something like that. And then if we were to draw one representative shell, the shell is going to go from, basically it's going to go from the center out to the side. So one shell, let's just pick something in the middle here, starting there, is going to wrap itself around like that. And then of course it's a shell of a cylinder, so it's going to come down like that. So this piece is going to be the cylindrical shell portion. See the best way to do that. And then of course we've got the hole cut out of this thing in the middle, which I did not draw, so let's see if I can kind of backtrack that a little bit. And have your shell looking something like that. Somewhat like that. So here is our cylindrical shell. You got your thickness here all the way around this thing right there. So there's your cylindrical shell. Okay, so we're going to go ahead and find the volume. So remember that this was 1, this was 2. So remember that the volume of a cylindrical shell is the circumference times the height times the thickness. The circumference, let's go ahead and put our integral here, the circumference of this thing is 2 pi r. But the r, or the radius of this, goes from the center, right here, out to here, somewhere right in the middle of the shell. That is an x value of some kind. So it's 2 pi x. Okay, that is your circumference. The height is defined by the curve, by the function. So the height in this case is x cubed. So x cubed. And then the thickness is some kind of a change of r, but remember that the radius in this case is x, so the thickness is just dx. So once again, just to make sure that we see this, this is the circumference, this is the height, this is the thickness. Again, think about it. You're just really finding the volume of a shell of a cylinder. Circumference times height times thickness. And it's going to go from, it looks like, what do we say? It's 1 to 2. 1 to 2. So this one really shouldn't be too awfully difficult for us to figure out. 2 pi is a constant. it can be pulled out to the front. Integral from 1 to 2. X times x cubed is x to the 4th dx. So that's what we're going to integrate to find the volume here. So we're going to have 2 pi. Integral, or antiderivative of x to the 4th is 1/5 x to the 5th from 1 to 2. So it looks like we're going to get 2 pi fifths. That's the constant. And then if I plug 2 in for x, 2 to the 5th power, 2, 4, 8, 16, 32. Minus plugging 1 in, we get 1 to the 5th, which is 1. So we're going to get 31 on the inside there. 31 times 2 is 60. Oops. 31 times 2 is 62. So it should be 62 pi over 5. That is your volume. Some kind of cubic, whatever it is, would be your units, depending on if they gave you units or not. Okay, so let's go ahead and take a look at the next example. All right, second example, use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the given curves about the y-axis. So once again, we're going to revolve this around the y-axis. Let's go ahead and sketch what these curves look like. So y equals 4 minus x squared. So in order to sketch that one, hopefully you realize that it's an upside down parabola. It's definitely quadratic and it opens down. If you did a little bit of quick work up here, we can put this up here on the top. Y equals 4x minus x squared. We want to find out where this thing hits the x-axis. So if we factor out the x there, you're going to get y equals x times 4 minus x. Hopefully you can see that your x-intercepts then are 0 and 4. So we're going to have an x-intercept at 0 and x-intercept out at 4. So it looks like this parabola right here is going to do something like this. Technically it keeps on going. Oops, sorry about that. Technically it keeps on going. Whoa. Let's see. There we go. Let's try that again. Still getting used to this new pen. Okay, so there's our parabola. Y equals x is, of course, is just your 45-degree line. Goes like this right to the origin. So you should be able to see the bounded region here is this area right in here. And this was a little bit different because we haven't actually done one like this yet where we've had a bounded region. So all it's going to do is it's going to create a height where the height of this thing is actually going to be the difference between the two functions. Just like finding area between curves. You're trying to find the height of this. Well, f of x in this case is defined to be the difference between the two curves. So let's go ahead and sketch what this will look like on the other side. Looks something like that. Something like that. And then, of course, this thing is going to have a top, and then it's going to have an inside part. So one representative cylinder is going to look something like that, with an inside piece like that, something like that. So here we're going to have our cylinder. There's our cylindrical shell. The radius is going to be some kind of an x value. Radius is going to go from the center out to wherever this thing hits. Right there, it's going to be some kind of an x value. So we do need to find the intersections, though. We do need to find, it's going to go from here, which is obviously 0, out to here. We have to figure out what that x value is right there. So if we set those two equations equal to each other, we're going to have 4x minus x squared equals x. We have to figure out what the x value is here. So we'll subtract x on both sides. We get 3x minus x squared equals 0. Factoring out an x. So it looks like we're going to get x equals 0, which we knew, and x equals 3. So those are our bounds. So let's go ahead and set up our integral. The volume is going to go from 0 to 3. Remember, it's circumference, which is 2 pi r, but in this case, r is x. just the radius, which is the x value, times the function. Now remember, here's where it is. The function here, the height, is going to be the difference in between these two. So the height is going to be defined by, the difference at anywhere on this thing. So in my particular shell, that's the height. It's not actually the entire shell. It doesn't always go all the way down to the axis. So the height here is going to be the difference between these two. So the height is the top one, which is the 4x minus x squared, minus the bottom one, which is minus x. Okay, that's the height. And then dx, of course, is our thickness. So now we're going to have to go ahead, and the first thing I'm going to do is we're going to simplify a bunch of this all at once. I am going to pull out the 2x, the 2 pi. Still have the integral from 0. I'm just going to rewrite that. Okay. So we'll pull out the 2 pi, still have the integral from 0 to 3. Okay, I'm going to go ahead and simplify the inside of the parentheses. So that's going to be 3x minus x squared dx. And then we're going to distribute the x through so that we can go ahead and take the antiderivative here. So 3x squared minus x cubed dx. Now we're going to go ahead and work out the integral here. So our volume is 2 pi. Now the antiderivative of 3x squared is just x cubed. Antiderivative of x cubed is 1/4 x to the 4th. And we'll evaluate that from 0 to 3. If we plug in 3, we're going to get 27 minus 3 to the 4th is 81, so 81/4. If I plug in 0, 0 makes x cubed and x to the 4th go away, so I don't have to worry about subtracting anything there. So looks like we're going to have to put all of this stuff into terms of fourths. Probably be the easiest, it looks like. So let's see, 27/4 is going to be, what is that, 54, 108 fourths minus 81 fourths. So we get 2 pi, so 108 minus 81 is 27. Yeah, that sounds right, 27/4. If I multiply the 2 pi in there, I'm going to get 27/2, so it should be 27 pi halves for our answer. So we get 27 pi halves, if I did that correctly. Does that look right? I think so. Okay, we'll come back and we'll do example 3. All right, example 3 is actually really short algebraically, so let's go ahead and work this one out. Use the method of cylindrical shells to find the volume generated by rotating the given region bounded by the given curves about the x-axis. So this time we're going around the x-axis. It doesn't change a lot, but it does change just a little bit. First of all, it's obviously going to change what we're rotating it around. But so let's see, we get y equals the square root of x, which looks like this, bounded by x equals 0 and y equals 2. So be careful on this one, because a lot of times people get this region wrong. X equals 0 is the y-axis. Oops, it's this. And then x equals 2. Y equals 2 is this horizontal line up here. So this is our region right there that we're actually going to rotate. We're going to rotate that around the x-axis, so we're going to go this direction. So if we were to kind of sketch what it looks like on the other side, looks something like that. So in this case, our shells, our cylindrical shells here, are actually going to go this direction, hollowed out there, but they're actually going to go this way. So that's going to make the problem just a little bit more interesting. So now this thing actually has to be in terms of y instead. So we actually have to take the equation y equals square root of x and solve this so it's now a function of x equals, well, that just means square both sides, so you get y squared equals x. So we know that x equals y squared. Basically, that's going to create our height of our shell. X equals y squared is this distance right here. from here up to there. That is now your function. That is now the height. So in this case, our radius now, which goes from, let's use blue, it goes from here out to here, is a y value. So the radius is a y value. So our volume is going to be 2 pi instead of x, it's going to be 2 pi y, because the radius is now a y value. And then the height of the function is now going to be y squared. And then now, because the thickness is going in the vertical direction, it's now dy, since the radius is now y. So now we just have to figure out what this goes from, and it's pretty much laid out for us here, because this is 0. They told us that this is y equals 2, so we're going to go from 0 to 2. So let's go ahead and simplify. This volume should actually be very simple to do. So it's 2 pi integral from 0 to 2 of y cubed dy. That's a y, believe it or not. Let's make that a y, because I can. There. All right, so we're going to get 2 pi 1/4 y to the 4th from 0 to 2. Okay, 2 pi times a 4th is a pi halves. Plugging in 2 into y to the 4th, 2, 4, 8, 16. Plugging in 0 gives you nothing. So we get 16 minus 0, 0 times pi halves is 8 pi units cubed. That is the volume. All right, one more to go. All right, example 4. Use the method of shells to find the volume generated by rotating the given region bounded by the given curves about the specified axis. So we're going to take the equation. Let's see if we can get that sketched here. Y equals the square root of x, which looks like that. Bounded by y equals 0, which is the x-axis, x equals 1, so we'll call this x equals 1. But we want to revolve this thing around the vertical line x equals negative 1. So that is now our axis of revolution. So we want it to go that direction. So that means on the other side over here, it's going to be a space of a couple of units. I did not leave myself enough space to do this very well. It's going to look something like that. I'm really not drawing that to scale. I apologize. But what you can see is that now I have a much wider open space here for my cylindrical shell. So it's going to go something like this, something like this, something like that, and then the shell is going to come down right there. The difference here, the main difference, is the radius. Okay, normally a radius is measured, the radius is always measured from the axis of revolution. So the radius here goes from here all the way out to here. But from the y-axis, which is right here, out to here, that's x. Okay, that's your x value. The problem is we've added an extra whole unit right here. That's a whole extra 1. So the radius of this thing is actually not just x now, it's x plus 1. That's the important part here. The radius has been changed by a unit, because remember, x is measured from the y-axis. That's how x is measured. That's an x distance. We added the extra 1 unit because of where we're rotating this thing. Nothing else really changes here in this case. The height of this thing is still going to be your function, which is y equals the square root of x, and the thickness of each one of these pieces is still just going to be a dx. So let's go ahead and integrate this. So we're going to have the volume, which is going to go from, looks like this goes from 0 out to 1. 2 pi r, our r value is x plus 1, so it's 2 pi x plus 1 times the height, which is the function square root of x, times the thickness, which is dx. All right, so let's go ahead and work this one out. So bring the 2 pi out to the front. Let's distribute the square root of x, which is x to the 1/2 power. So x times x to the 1/2 is x to the 3/2, plus 1 times x to the 1/2 is x to the 1/2 dx. Let's take our antiderivatives. So the antiderivative of x to the 3/2 is x to the 5/2 divided by 5/2, but that's multiplying by 2/5, plus x to the 3/2 dividing by 3/2 is multiplying by 2/3, and we'll evaluate that from 0 to 1. So if I were to plug 1 in, we're going to get 2/5 times 1, which is 2/5, plus 2/3 times 1, which is 2/3. And if I plug 0 in for the x's, those both go away, so we're good to go there. So now we're going to have to combine 2/5 and 2/3. It looks like the common denominator there is 15ths. So the first one here, multiplying by 3 over 3 is going to give us 6/15. Multiplying the second one by 5 over 5 is 10/15. So adding those together, I get 16/15. Multiplying that by 2, it looks like we get 32 pi 15ths units cubed. And there is your volume. All right, that was a little over 20 minutes, so I apologize. Again, I wanted to keep that under 20, but close enough. All right, you should have enough information to do any of the problems. If you have any questions, feel free to ask.